So I'll go ahead and get started. My name is Marina Metes, and I'm with the U.S. Geological Survey. And my presentation is on mapping stream and floodplain geomorphic characteristics with the Floodplain and Channel Evaluation Tool, or FACET. And so I just want to start by acknowledging my co-authors, Chrissy Hopkins, Labib Ahmed, Peter Claggett, Tim Lamont, and Greg Noe, and just our various funding sources to make this work possible. And so I'm based in Baltimore, Maryland, in the United States. And so this work that's presented here is based in the Mid-Atlantic region of the United States within the Chesapeake Bay and Delaware River watersheds. And so this work was really motivated by another project where we had 68 field sites across these two watersheds to measure stream characteristics such as stream bank height, channel width, and floodplain extent in the field. And the goal of that project was to measure rates of stream bank erosion and floodplain sediment deposition and associated nutrient fluxes with those processes. And so through that work, we knew that there was a need to be able to measure these stream bank characteristics at the watershed scale so that we could model sediment and nutrient fluxes across a larger watershed scale. And so LiDAR was available for the majority of these two watersheds. And so this map here just shows the availability of LiDAR, with the gray areas just being the areas where we don't have LiDAR available. And so this, there's many data sets that make up the LiDAR availability for this large region, and the range of years is between 2005 and 2018. So you can imagine there's a range of LiDAR accuracies with these various data sets, and some DEMs were only available as high of a resolution as 3.4 meters, and some are as high as 1 meter. And so we resampled all of our DEMs to 3 meters and mosaicked by watersheds that averaged about 400 square kilometers in drainage area. And so we developed the FACET tool, which automates measuring fine scale geomorphometry. So this is an open source Python-based tool, and there's a link where the code is available on our repository. And the tool inputs include a digital elevation model at 3 meters or finer, an existing stream network, and an optional road, rail, or culvert layer, and then various user-defined parameters that will vary based on regional setting. And so our tool outputs are stream bank locations, and we have two different methods of measuring stream banks. And then with that, we have measures of bank height, channel width, and other channel metrics. And then FACET will also delineate the active frequently flooded portion of the floodplain and output floodplain width, and then also summarize channel and floodplain geomorphometry at the reach scale. And so the input data sets are a raw digital elevation model, a road and railroad layer, or a culvert layer, and an existing stream network. And so these layers are necessary to first hydrologically condition the DEM if you don't already have one that's hydrologically conditioned. And so we identify road, rail, or road stream and rail stream intersections and breach the DEM at that location. We also use the breach depressions tool within Whitebox tools to resolve any remaining pits in the DEM. And then we generate our own stream network that follows the contours of our digital elevation model using TauDem tools. And so we're using the D8 flow direction, D8 contributing area, and the stream reach and watershed tools to generate our stream network and catchments. And then we are also using the height above nearest drainage grid to help with delineating our floodplain extent. And we're using this, the TauDem D infinity distance down. And the height above nearest drainage grid is essentially a way to set each pixel on the landscape as a vertical distance or a depth between that pixel and the point on the stream network to which it drains. And so I'll get into a little bit more detail on that shortly. So the first method of identifying stream banks is through this cross-section analysis. And so this image on the left here shows cross sections that are drawn fairly frequently across the entire stream network. These are spaced every 9 meters apart. And so this is just an elevation profile that's pulled out of one of these cross sections. So to identify the stream banks, we start from the bottom of the profile, which we assume to be the bottom of the channel, and measure the width in these vertical increments moving up. And a ratio is calculated between each width measurement and the next highest width. And until a ratio exceeds a user-defined parameter. And so you can see the width between this vertical increment here and the next highest one is much larger. And so this would exceed our ratio. And so within this region is where FACET will search for the actual stream bank location using a slope threshold. And so if we have, such as in this case, banks at differing elevations, FACET will identify the lower of the two stream banks. And so then on the left here is just showing at each one of these cross sections, the bank point pairs that are identified. And then we can calculate various channel metrics with this information, such as channel width, bank height, and bank angle. And so here's just an example of what this looks like at a small scale, where the red bank points are areas with a much larger bank height, and then the blue and green and yellow bank points are areas with a smaller bank height. And so this just kind of shows you an example of sort of a stream going through a more agricultural area, and then as it moves downstream into this more urban area, we see much larger bank heights, which is a pattern that we would expect to see if this channel is getting more incised in this urban area. But this just gives you an idea of the detail that we can see being able to measure this information at such a fine scale. And then we also use a raster-based method to identify stream banks. And so we do this as a way to get a more continuous depiction of the stream banks using our DEM. And we use a wavelet-based curvature to identify possible bank points, And so after we calculate curvature, we have these moving windows that traverse the stream network. And for each window, pixels that exceed 30% of our maximum curvature within each window are identified as possible stream banks. And then to identify the actual bank location, since we might have cases where there's like a terrace or some other feature that might get identified as a bank pixel within these moving windows, we start from the stream channel and move outward in parallel lines adjacent to the stream channel and identify the location where we have the majority of bank pixels. And so then once we identify the point moving outward from the stream channel where we have our stream bank, we can measure our channel width. And so these metrics are then, for channel width, are summarized at small channel segments along the stream network. And so the last component of FACET is to measure the floodplain. And so we're using the height above nearest drainage grid, which you can see an example of here, where just the value along the stream network is 0. And then each of these stream pixels, the blues being lower values and the reds being higher values, are just the vertical distance between each pixel and the stream network. And so we used our field data to calibrate our model. And so in the field, we identified the active, frequently flooded portion of the floodplain based on field evidence of topography, changes in vegetation, and evidence of recent flooding. And so at each field site, we identified the hand threshold that corresponded with our field measured floodplain extent at each site. And we built a predictive linear model that related the hand height threshold to drainage area. And because we had our field sites spanning these 5 different physiographic provinces within the Chesapeake Bay and Delaware River watersheds, we tested out the model for each of these 5 regions. And we found that there was not a significant relationship between the hand threshold and drainage area for 2 of our 5 provinces. But for the remaining Piedmont, Valley and Ridge, and Appalachian Plateau, there was. And so FACET uses this linear model that relates the hand threshold to drainage area to delineate the floodplain extent. And then for the 2 sites where we didn't have a significant relationship, we used the mean hand threshold from our field sites. And so this is the output of our floodplain. And then we also draw cross sections along each reach to pull out channel or floodplain width. And so just going back to an overview of all the components of FACET with our cross section analysis and our raster-based analysis to measure channel geometry, and then our hand-based approach to measure our active floodplain extent. And so we used our 68 sites to also measure our FACET accuracy. And so these sites ranged in drainage area from 3 square kilometers to about 3,000. So we had a large range of stream sizes, and we also had representation from multiple different land use types. And then so our field measurements included bank height, channel width, and floodplain width. And we ran FACET on 3-meter DEMs, but where we had 1-meter DEMs available, we also tested the FACET accuracy with 1-meter DEMs. And so for channel width, these graphs are just showing the difference between the FACET values and the field values, with a positive value being an over prediction by FACET and a negative being an under prediction. And on the left, we see the outputs from the cross-section method, which tended to almost always over predict channel width more in smaller drainage areas, and then only really started to under predict in larger drainage areas. And we saw 3-meter DEMs. And not so much of a difference between the cross-section and raster-based methods with a 3-meter DEM, but with a 1-meter DEM, the raster-based method did have a slight improvement. And with the bank heights, we didn't really see much of a change, a slight improvement with 1-meter DEMs, no clear pattern of under or over predicting at various drainage areas. And with the floodplain width, we actually had a slightly higher accuracy with 3-meter DEMs. And then because we had so many different LiDAR data sets that we compiled to run FACET, we were really curious to see if there was an influence of LiDAR accuracy on our FACET outputs. And we did see however, we did not see that much of a difference with our bank height and floodplain width accuracies with higher quality LiDAR. And we were also curious about the influence of vertical accuracy on bank height accuracy, and we didn't see much of an influence. And so just to summarize, FACET is an open source tool that calculated stream channel and floodplain geomorphometry, and channel width was most sensitive to DEM resolution and LiDAR accuracy. And we're currently working on methods to improve our floodplain mapping and expand this outside of the Mid-Atlantic region of the Chesapeake Bay and Delaware River watersheds. And with that, if there's time for questions, I'd be happy to take a question or two.